have one final topic today, and it's a real-world problem based on Newton's law of cooling. So I'd like for you to pause the video for a minute and go ahead and write Newton's law of cooling and what each of the individual pieces means, and then we'll come back and talk about it. So Newton's law of cooling says that T, our final temperature, is equal to our initial temperature T naught minus the temperature of our room or our surroundings if we're outside. That's in parentheses, multiplied by E. Remember, that's our natural base. It is a constant. And we're going to raise that to the negative R times T power, with R being our cooling rate and T being some amount of time. Could be minutes, hours, days, whatever. And then notice at the very end we have our room temperature tacked onto the end again. So it occurs twice in the equation. Let's look at our actual problem and go ahead and fill in all of our variables as we go along. So we're cooking a leche, which is an Ethiopian stew. And when you take it off the stove, its temperature is 212 degrees Fahrenheit. In other words, it's boiling, right? That's the temperature that water boils at. The temperature of the room is 70 degrees Fahrenheit, and we're given a cooling rate of the stew equal to 0.046. That rate is in degrees Fahrenheit per minute if our time is in minutes. We want to go ahead and figure out how long it's going to take the stew to get to a serving temperature of 100 degrees. You don't want to burn your mouth with boiling stew. You want it to be a little more moderate, about just a little over your body temperature. So we want our final temperature to be 100 degrees. We know that our initial temperature is 212 degrees, and the room temperature is 70. Our rate of cooling, 0.046, and our time, well, that's what we're trying to figure out. So put a big question mark there. Let's plug in what we know into this equation so that we can solve for time, the one thing that we don't know. So we have 100 is equal to 212 minus 70. Remember, that's T naught minus T of our room. And that's multiplied by E raised to the negative 0.046. Please don't forget the negative here, it's important. And that's going to be times T. And then we add 70 at the end. So the goal is to solve for T. The first thing we want to do is work on isolating this term, just like we kind of did previously. We want to make sure that we get the thing that has the base of an exponent raised to an exponent by itself. And we'll do a little simplifying as we go along too. I'm going to move 70 to the other side with the 100. That'll give me 30. And that's going to be equal to, let's go ahead and do this math. 212 minus 70 is 142. And then we have E to the negative 0.046 times T power. All right, continue isolating our exponent base. So I want to divide by 142. After I divide by 142, I will have my natural base E that is isolated. Let's go ahead and rewrite this to make it clear. And as I rewrite it, I actually want to swap the right side and the left side. If I'm going to swirl, remember that I need my exponent base raised to the exponent to be on the left-hand side. E to the negative 0.046t is equal to 30 over 142. And now I can go ahead and swirl. Remember that if we have a base of E on our exponent, then that's going to be a natural log. Whenever we write the log, it's a log base E, but we write that as ln for natural log. So natural log of 30 over 142 is equal to negative 0.046t. And now we've almost got t isolated. Remember that this is a number. We're just going to plug that into our calculator to get the number. So divide by the 0.046 or negative 0.046. And whenever you plug all of this into your calculator, be sure you put the natural log button, and then in the parentheses say 30 divided by 142, close up that parentheses, and then divide by your rate of cooling, or the negative of that. And when you do all of that, you should get T equal to about 33.8 minutes.